Hello, everybody. My name is Zach Brumbach. I'm here today to talk about ECE 3710 Intro to Circuits and Electronics at Georgia Tech. This is Linearity and Superposition. This is 2.13. So first, let's talk about what does it mean to be linear in the first place. So as some of you may know, I've taught linear algebra in the past. This is one of my favorite things to start the class with talking about, is what makes a function actually linear. And a lot of people assume that something like this would make something called a linear function, but actually this isn't a linear function. We call this affine. Okay, something that is linear is something that requires a few special things that we'll talk about, but one of them is that it does in fact touch the origin. This is linear. So some common examples of what you may know as linear functions would be like the derivative, right? d over dt. If you have a few things, you can separate them out, and you can combine them. The derivative 0 is 0, stuff like this. Also, you have the integral. These are more calculus-based stuff. And something that some may be more familiar with is the Laplace transform. These are all linear things that we use to kind of separate out equations and look at them in parts that we can break down a little bit more easy. Okay. So what this looks like for this class, we start with the big function v equals I r. Okay. This is your linear equation that we'll be talking about. This is Ohm's law here. Okay. And the reason that this is linear, not affine, is because there's no like plus something. Okay. It's just an input times a constant equals an output. Okay. So when we're talking about linear systems, there are three qualifications that make something a linear function, a linear system. Okay. First is that it contains the origin. What this means in this case is that if we have zero current going in, we're going to have zero voltage. Okay, that makes sense. There's no electrons passing between something. There's no potential difference between those two things. Next one is that we're closed under addition. Okay. And what that means is if I have some voltage, which gives me some current times some resistance, and I have a different source that gives me a different current, if instead I make one big voltage source, and I'll show you what this looks like in a minute, which is V1 plus V2, then it's going to give me a current of I1 plus I2 times R. Okay, so essentially what this means is if we have two sources applying to the same component, we can superimpose them, which is what this is called right here. We can add them together based on their individual contributions. Condition 3 is that we're closed under scalar multiplication. What that means is if I have some voltage in and I multiply it by 4, so if I go from 1 volt to 4 volts, I have 4 times whatever my original current is times my resistance. Okay. So it'll always, if we increase our voltage, our current will increase proportionally. Closed under scalar multiplication. So what this looks like in an actual circuit, for instance, is if I had a circuit that looks like this. Okay, with 3 resistors. Call this a 5-volt supply. Okay, and the voltage from here to here is 2 volts. And I also have, if instead I were to supply this with something maybe a little more typical, like something we haven't talked about yet, but we will get to. For instance, 15 volts with a time-dependent component, 15 times cosine. So we're getting a sinusoid voltage here. And we have the same circuit. Okay. And here, instead, we got 6 cosine of t volts. Okay. Then instead, if I superimpose, which is linearly adding these two things, and I had a voltage source that was 5 plus 15 cosine of t, okay? Then if I have the exact same circuit, oops, geez. Okay, then I don't need to do any math with this new source. I just know it's two components, and I know that the voltage across this will be 2 plus 6 cosine of t. Okay, so this is what it means to superimpose, all right? And to see what it would look like for closure and multiplication, say we have another 5-volt source. Same sort of circuit. And let's call this now 3 volts, just a different circuit. And then instead we have a now 50-volt source. Then the voltage across this is now 10 times. So the exact same proportion here is to here. So this is 30 volts from here to here. Okay, so this is your multiplication. This is your addition up here, all right? These are the things that make these systems linear. So how can we use this? Well, we can use this in a more complicated circuit with a whole bunch of different sources. Say we have something that looks like this. Current, let's call this over here resistor. Over here we have another voltage source. In the middle we have another resistor, and from here we have a resistor in parallel with the current. Okay, and say we wanted to find the voltage across this. Okay, called VR. This is something that's a little bit more complicated that maybe mesh and node analysis won't get you easy answers for. And what we do is we break this up into smaller, more digestible components with linearity. So we take it one source at a time. So here we have 3 sources, okay, 2 voltage and 1 current. And what we do to linearly break this down is we look at them again, one at a time. And I'll write the steps out, and then I'll do it for this example, okay? Or at least I'll draw the equivalent circuits. So the steps will be as follows. Number 1, 0 all sources, but one of them, okay? Step 2, actually, one little note on that is let's remember that a voltage source with 0 volts is equivalent to just a wire, and a current source with 0 amps is equivalent to an open, or breaking the circuit where it was, okay? So if it's a voltage source, you draw a line through it. If it's a current source, you break it. And these are for the components you're not looking at, okay? Step 2 is you find the contribution from that source. Step 3 is then we repeat for each source. And step 4 is where we superimpose using linearity. And we add contributions to get total. These are usually voltage or currents, V or I, whichever one they're asking. Remember, knowing Ohm's law, you know one, you need the other. So for instance, if we're doing this for a component or for source 1, so we 0 all sources but 1. In this case, we're keeping source 1, okay? The resistors don't change because they're not sources. Our current source here is going to be an open. The resistor doesn't change. And then our voltage source is going to just be a short, okay? You're looking for the voltage across this. So now this is a more maybe a way you've probably seen this a little bit easier is if we draw the circuit like this. Now knowing that the current source is open. Something like this, we can pretty easily using some resistance rules, break down and find what VR is due to this one source, okay? And I would do this using mesh or node analysis is the way I would get this done. So I would probably do this one using mesh. So we would pick a circle, call this I1, pick a circle, call this I2. And we would break this down to solve for the current through this resistor to find the voltage from source one, okay? So what we're doing is that we're breaking up this big circuit into different components that we can then use mesh and node analysis to make this easier to do, okay? We were to now do this with source two. Our first source being open. Source two is still there. A resistor here. We have a resistor here. Our current source is still an open. This resistor is still here. And this resistor is still there. And we're once again looking for V from R from the second source. So this is the same sort of thing. We would break this up using mesh or node analysis, whichever you prefer. Go from there. And then for the third step, and this is something that I will give you a lot for your worksheet for those who are in my class who are seeing this. This is something I'll give you to work on Friday. So for source three here, we're keeping our current source. Okay. So we have a resistor here. V1 becomes a short. Let's zoom this out for a second. V2 becomes a short. It's a bad line. Here's our resistor of interest or the voltage. There we have it. Now we have a current source and just a pure resistive circuit. These are things that we can solve pretty easily. And then to get the total, to find what our original VR was, we just add all these together. So we get VR is equal to VR from source one plus VR from source two plus VR from source three. Okay. So again, this is literally breaking it up piece by piece, and I'll give you guys some easier ways to see this on Friday. Okay, so some actual practice problems with this. But it's very important to understand these steps. You zero all of your sources but one. You find the contribution for each source, and then you repeat for each source. And then at the very end, you add all of those to get the total voltage or current through a resistor. So that's what linearity and superposition are. Sorry, just one moment. Okay. Something else I wanted to do here was I wanted to talk about the last worksheet. So that concludes the actual lecture part of this. Documents, desktop. So I gave you all a rather difficult worksheet last week, which not a lot of people finished, which is okay. Come on. These are meant to be very intensive, and if you understand them, you understand everything that's going on. So let me go through the last one. Here we go. It's number 6 worksheet. So person says find V1 and I1 using mesh. And then I said in class, this should be mesh or node analysis, whichever way that you want to solve it. And looking at this, knowing linearity and superposition now, we could actually break this one down using linearity to solve this from each contribution and then solve it from there. So the way I'll do this, I'll do this first one with node, and I'll just do the second one with mesh analysis. Okay. So node analysis, remember, define a ground node. and name your nodes. We'll call this node A. We'll call this, and remember, a node is everything not separated by a component. So this whole thing is node B. This whole thing is node C. Okay. All of this down here, we designate to be ground. The circle is here. Okay. So what we do in node analysis is we try to find the voltage at each of these nodes. All right. So we'll look for VA. We'll look for VB and VC. These are the voltages at each node. Okay. And something to note here is VB is equal to V1, which is what I'm asking you here. Find the voltage through V1, or the voltage at V1 with respect to ground, and the current through that resistor, which we'll talk about after we do the node analysis to find that voltage. All right, so VA is actually rather straightforward here because across from ground, we have a 16-volt source. It means VA is just 16 volts. Likewise with VC, we have an 8-volt source, but it's backwards, so the negative. So it's going, the difference from here to here was 16 volts. Here, the difference from here to here is 8. We're going backwards, so this is minus 8. You can also just note that from the negative being pointed up. Okay. So from here, we minus 8, and we get this as negative 8 volts. Okay. So hey, we have 2 over 3 nodes. That looks like pretty easy so far. So now let's actually do the node analysis, which node analysis, if you recall, is the sum of all in currents equals the sum of all out currents. Okay. All right. So let's define this current as going in through this resistor, this one going in from this resistor, and this one coming down. All right. So we have 2 currents coming in, which I'll call this R1, R2, R3, and R4. Okay. So we have this current coming in plus this current coming in on one side. And if we have V equals IR, means we also have I equals V over R, which is how we're going to write our currents for node analysis. So we're looking for the voltage across that resistor times over its resistance. So the voltage from here to here, plus and minus, plus and minus, plus and minus. We'll call this one plus and minus as well. Okay. So the voltage, let me erase some of this stuff. Okay. The voltage from node A to here across the resistor is VA minus VB. That's the voltage across that resistor divided by its resistance, 500 ohms. Okay. Plus, going over here now, across this resistor from here to here, which is now VC, minus VB over 500. It's equal to the currents coming out, which are, let me erase these big nodes, I can move away a little bit. Which looking here, we have this minus this, where the minus is 0, so now we just have VB minus 0 over R4, which is 500. Plus, from here, it's exactly the same across the nodes, right? So this one is also VB minus 0 over 1500. Okay. And from here, we have one equation with one unknown, right? Because we know VA is 16 and VC is 8. So we can rewrite this as, it's over here. We have 16 minus VB over 500 plus minus 8 minus VB over 500 equals VB over 500 plus VB over 1500. From here, what I'll do is I'll multiply everything by the greatest common denominator, which is 1500. So we're going to multiply everything by 1500 to make this look a little nicer. So we're going to make this first one's going to be, this 1500 over 500 becomes 3. So this becomes 48 minus 3 VB minus 8 to 3 is 24 minus 3 VB equals 3 VB plus VB. And from here, we solve this to get us VB is equal to 10/24, okay? And this is equal to my V1. Because up here, we look back at the question, we specified V1 to be the voltage at this node. That's what we were looking for in the first place, right? So we have V1. Great. Now let's find I1. The easiest way I would say to, the easiest way I would say to do I1 is to do just the voltage drop across the resistor, which we know is V1 to ground. And we'll use Ohm's law to do V over R is equal to I. So we get 10 over 24 over 500. And we can just leave it like that. And we're done. We can simplify that a little bit, but yeah, that's it. Any questions about that? This will simplify to, what's 5/1200ths? Oh, 1 over 1200. There you go. Amps. So that is your I1 there. Okay. So that is how we would solve something like this with node analysis. And I'm going to skip this second one for right now, just due to the time. I'll post my solutions to this in the next few days, very clear right now for all y'all. So looking at this one here, now we're talking about our Thevenin equivalence. So it's looking for V in R Thevenin and I short circuit. So remember the way to do this is first to find R Thevenin. You zero all of your contributions. So to do that, with this first one to find R Thevenin, okay, we're going to make this 0, and we're going to find the equivalent resistance from A to B. So let me redraw the circuit. We have 600, 600, 600, 600, 600. Here we have B, here we have A. The equivalent from here, these two are in series. Okay, so these become 1200 ohms. These two are in parallel, and there are two nodes with the same resistance, so these become 300 ohms. So now we can rewrite this as A B. This one's 600, this one's 600, this one's 300, this one's 1200, and this is equivalent to this. So we equate these two in parallel. This becomes 400 ohms. This becomes 400. Becomes 6. This was and stays 600. This was 300 from A to B. And now the equivalent resistance, you can clearly see, not our equivalent or Thevenin, is equal to, these three are in series, so we add them, so they become 1300 ohms. Okay. Now, looking at this, we find V Thevenin. And remember, if you know V Thevenin and R Thevenin, you can find ISC just through Ohm's law. Okay. So let's find the equivalent. Let's find V Thevenin here. So we have our 10-volt source. We have resistor here, resistor here, resistor here, resistor there, resistor there. This is B, this is A, this is my last resistor. Great. Remember that all of these resistors are 600 ohms. So when we're looking for V7, we make these an open, all right? So what that looks like, there's no current going here, okay? There's no current going through this. There's not going to be any voltage drop across this resistor because it's just hanging out on a ledge. So this voltage is also just A in terms of voltage, all right? And that's because that resistor has no voltage drop, because there's no reason for any current to want to go over there because it's just a dead end. Same sort of thing for B here. Even though we have two ways to B, nothing is going to want to go this way if it can just proceed this way where current is going to want to go. It's just two resistors leading to a dead end versus a wire that goes to other places. Nothing is going to want to go through there. Thus, this node is equivalent to the voltage at B. Okay. Now we have a much simpler circuit that we can look at. Here we have, again, 600, 600, and 600. This is 10 volts. So here is A and here is B. And we can just use a simple voltage divider to get 600 over 1800, our total equivalent resistance, times 10 to be my voltage from A to B across the 600 ohm resistor. So that gives me 3.3 volt, 3.3 repeating volts for V Thevenin. So what this whole circuit is equivalent to at A and B, if that's where we're looking, what A and B see when they're connected to this is just a simple voltage source, 3.3 volts in series with a 1300 ohm resistor. That is what this is equivalent to for A and B. Okay. All right. This last one is a little bit more complicated. Okay. And that's okay. Still something that we can do here. So looking at this, what we have is we're first going to find R7. To do this, remember, you zero all of your sources first. So let me redraw this. And here we have A. Here we have, that's an answer. B. Okay. So here, again, my voltage sources become a line, a short, and my current sources become an open. You can see that here and here, okay? Great. So now let's find the equivalent resistance between these two. All right. So another way that I'll rewrite this is just a bunch of hanging wire out here at the bottom. So I'm just going to call this here B. So I'm going to do B. So we're just trying to find their equivalent resistance here. So when we do this, take it one step at a time. These are in series. These are in parallel. For these two in series are going to be 155 ohms. And this one over here is going to be 30 ohms. When you do your series and parallel resistor equivalents. So now we have B. Move over a little bit. Now we have 155. This is 660. This is 30. And this is B. So now what I would say we have is we have these two in parallel, and that's it. Nothing else is in parallel or in series clearly, okay? It may look like they are, but they're not actually in series or parallel because they need to have, they aren't, for instance, these two are in series, but we need to look at the nodes, so we're not trying to combine them, okay? But remember, series is literally a straight line with nothing connecting, resistor, resistor. Parallel is two opposite nodes with only the resistors. So here we have from this node to this node, both resistors share those nodes as their ends, so they are in parallel. Here the equivalent here becomes A, B, 30, 60. This is 123.18. So now these two are in series. So this becomes 183.18. In parallel with 30. A. So we have one last parallel, sorry, set of resistors, which become from A to B, we just have a 25.72 ohm resistor. That great. This is about as hard as it gets, right? So this is a lot of information, but it is not something that you can't do. You have all of the tools to be able to do them. You just break it up into little bite-sized components and go from there, okay? So now let's look at finding VThevenin, okay? So move this so I can write close to this. So our Thevenin, remember that we keep this open between these two, and we look for the voltage between them, okay? That's what VThevenin is. Right now, the voltage between these two things. You could use superposition and break this up into. What I'm actually going to do here is I'm going to do node analysis. All right? So I'm going to set my ground node here. All right? I'm going to call this one over here, well, we'll call A, node A. Write these in a bolder color. Node A, B, node B. Call this one over here node C, and this node here node D, okay? So we're looking for VA, VB, VC, and VD, where VThevenin is equal to VA minus VB, the voltage difference between them. So we have VC is equal to 10 volts because it is a 10-volt source from ground. That one's easy. We know that from the get-go, right? So I'm actually going to, well, I'll keep it. That's the only one that's trivial here. We have a current from B to the ground, but we don't know the voltage. And what we're looking for is that voltage. So we're going to now do node analysis. So we'll start with VA, around node A, I'll actually call it. So we have to specify the directions of each of our currents going through here. And these are guesses, but you need to make sure they're consistent. So you need to specify them. So here, this one going that way, and this one going to ground. Great. So from here for node A, what we have is we have from node D to node A coming in, and that's the only one coming in for node A. So we have VD minus VA over 60. Going out, we have these two here, and these are VA minus VB over 40 for the one on top, plus VA minus VB over 120 on the bottom. Okay. And I'm actually going to reorganize this. So I'm going to put all of my variables on one side. This is going to be minus 1 over 60, minus 1 over 40, minus 1 over 120 times VA plus 1 over 40 plus 1 over 120 VB plus 1 over 60 VD is equal to 0. That makes sense why I'm doing this when it gets a little later. Next is node B. Okay. Looking at node B, we have going into node B, and just remember that node B here is all of this is node B, okay? Anything that isn't broken by a component, right? Going into node B, we have VD minus VB over 600. And again, remember the reason that I'm doing all of this is because we're counting currents going in is equal to currents going out, which V is equal to IR, not 3. This isn't equivalent. This is actually equal. So we have I equals V over R. The voltage difference over each resistor. That's what I'm doing here. That's the first one going in. Plus VA minus VB over 40. Plus VA minus VB over 120. And that's all going in. Coming out, we have 0.1 amps. And we also have VB minus 0 over 95. And I'll rewrite this instead as 1 over 40 plus 1 over 120 VA plus minus 1 over 40 minus 1 over 120 minus 1 over 600. Yeah, minus 1 over 95 VB. And this is plus VD is only with 1 over 600 VD is equal to 0. And that's node B. Node C, VC is equal to 10. Much easier. Last one is node D. Where we have VC minus VD over 60. Going in, and then coming out, we have sorry. Going out, we have VD minus VA over, where's that? Where I lost myself. Over 60. Plus VD minus VB over 600. And we'll reorganize this one to be instead 1 over 60 VA plus 1 over 600 VB plus minus 1 over 60 minus 1 over 60 VB equals 0. From here, we have 4 linear equations with 4 variables. So I can rewrite this as in a matrix minus 0.05, 0.03 repeating 0, 0 point repeating 0, 0.03 repeating minus 0.0455, 0, 0.0016 repeating, 0.016 repeating, 0.0016 repeating. Oh, sorry. That doesn't go there. 0, 0, 1, 0, 10. And this one is supposed to be 0.1. And what I'm doing here is, if you remember from linear algebra, I'm literally taking my coefficients, D, and plugging them into the A, B, C, B equals number. Okay, so I'm reorganizing this into a matrix. And then for the bottom one, we had 0.016 repeating, 0.0016 repeating, 0.016 repeating, 0.03. Okay. Yeah. Oh, I missed a part here. I'm sorry. This is supposed to be plus 1 over 16. BC here. Apologies for that. And then this is equal to 0. And if you put this in reduced row echelon form, you're going to get VA is equal to 0.902. VB is equal to minus 1.339. VC is equal to 10. VD is equal to 5.384. And remember, we're looking for V Thevenin, which is equal to VA minus VB, which in this case is 2.241 volts. That is a lot of math, and I know that. This is meant to be the most difficult types of problems that you'll see in these sorts of instances, okay? This is as hard as it gets. So, to redraw this equivalent circuit, so instead of all of that mess, if we don't want to analyze it again, what we can do is we can make this a 25.72 ohm resistor in series with a 2.241 volt voltage supply. All of that just to get it so we have a voltage and a resistor with respect to A and B. And that's it. I know this was a lot, and I may have made any small arithmetic mistakes. Feel free to email me. Otherwise, I hope you guys have a good class on Friday. We'll be there with a worksheet. That should be hopefully a little bit more straightforward. It'll be completable within the amount of time for class, and I'll take that and I'll go through everything over the weekend. So with that, again, email me if you have any questions about anything, and have a good rest of your day.